Our universe contains 2 trillion galaxies, each with a story to tell. This grand cosmic narrative is written in the collisions of giants, the birth of stars, and the silent pull of invisible forces. We are about to embark on a journey through 50 fascinating facts that reveal how these vast islands of stars are born, live, and ultimately die. By the end, you will possess a new understanding of our place in this breathtaking cosmic tapestry. We will uncover how an invisible scaffold shaped everything we see and witness the future collision that awaits our own Milky Way. What single cosmic mystery has always captured your imagination? Billions of years before the first star ignited, our universe looked nothing like it does today. It was not a vast, dark expanse dotted with glittering islands of light. Instead, it was a primordial sea, a hot and dense fog of fundamental particles and blinding light, so uniform that if you could somehow float within it, you would see the same featureless glow in every direction. There were no points of reference, no variations in density, not even atoms as we know them. This was the raw, unformed state of everything, a cosmic canvas waiting for its first brushstroke. The question then becomes, how did we get from that perfect, almost boring uniformity to the spectacularly complex universe of galaxies we see today? The answer lies in the faintest of whispers, tiny quantum ripples imprinted on that early fog. These insignificant flaws, these minute wrinkles in the fabric of space and time, were the seeds of everything. They were the universe's first and most important imperfections, the slight over-densities where gravity could finally get a grip and begin its work of cosmic construction. From this nearly perfect smoothness, the grand architecture of the cosmos would slowly emerge. Yet within that smooth cosmic sea, the seeds of structure were already sown. Those tiny quantum ripples, however, were far too weak on their own to build the magnificent structures we see today. They needed a powerful, invisible ally, a force that could amplify their faint signal into a gravitational command. This is where the universe's greatest mystery steps onto the stage: dark matter. This enigmatic substance is completely invisible. It does not emit, absorb, or reflect any light, making it utterly undetectable to our telescopes. Yet it is everywhere, a ghostly presence that makes up roughly 27% of the entire cosmos, far more than all the atoms and stars we can see combined. So how do we know it is even there? We see its effects through its immense gravitational pull. In the early universe, while normal matter was a turbulent soup of particles buffeted by the pressure of intense light, dark matter was calm and unstirred. It simply did not interact with light, allowing it to respond only to gravity's call. This made it the perfect cosmic architect. These dark matter particles began to gather around those initial quantum ripples, building up vast, invisible structures. They wove a hidden scaffolding, a three-dimensional web of gravitational wells across the expanding universe. This dark framework became the blueprint for all future construction. Ordinary matter, the stuff that would eventually become stars, planets, and us, was merely following the plan. As the universe cooled, this normal matter was drawn by gravity into the deepest pockets of this dark matter web. It flowed along the invisible filaments, pooling at the intersections to form the very first protogalactic clouds. Without this dark matter framework, the gravitational pull from the visible matter alone would have been far too weak. Galaxies might never have formed at all, leaving the universe a forever diffuse and dark expanse. The birth of every galaxy, including our own Milky Way, was directed by the hand of something we cannot see. The first galaxies to emerge from this dark matter blueprint were nothing like the majestic spirals we picture today. They were cosmic infants, small and chaotic, barely holding themselves together. Imagine a sprawling, turbulent cloud of primordial gas, only a fraction the size of our Milky Way, swirling within its invisible dark matter cocoon. These were the universe's first experiments in galaxy building, and they were wild, unruly places. Without the elegant structures of modern galaxies, they lacked defined centers or graceful arms. Their shapes were irregular and clumpy, more like messy puffs of star-forming smoke than the grand, organized systems that would come later. Within these chaotic nurseries, the first generations of stars were born at a ferocious, almost reckless pace. Vast reservoirs of fresh, pristine gas collapsed directly into monstrous, brilliant stars that burned hot and died young in spectacular supernova explosions. This was a universe under construction, a violent and creative period where the rules were still being written, forging the very first elements that would one day seed future stars and planets. Gravity is the universe's ultimate architect, a force of profound patience and power. We often think of it as the weakest of nature's fundamental forces, easily overpowered by a simple magnet lifting a paperclip. Yet on the cosmic stage, across vast expanses of space and time, its gentle, unrelenting pull becomes the dominant sculptor of reality. It never turns off. It never weakens over distance in the emptiness of space. This persistence is its greatest strength. For billions of years, gravity worked tirelessly on the faint wrinkles in the primordial universe, slowly and steadily amplifying them. It pulled the invisible threads of dark matter into its great cosmic web. Then it turned its attention to the ordinary matter, the gas that would become the stuff of stars and life. This gas began to drift, drawn inexorably into the deepening gravitational wells crafted by the dark matter scaffolding. What started as a faint whisper of attraction grew into a commanding pull, causing these immense clouds of gas to collapse in on themselves. This was not a sudden implosion, but a gradual, majestic gathering, a cosmic contraction that spanned epochs. As these vast reservoirs of gas collapsed, they began to spin and flatten, their internal pressure and heat building until the first stars sparked to life within them. Without gravity's patient, universal embrace, those initial seeds of structure would have remained just that, seeds. There would have been no collapse, no ignition, and no galaxies to light up the cosmos. Every spiral arm, every glowing nebula, and every starry disk is a monument to gravity's slow, quiet, and irresistible work. The chaotic infancy of the universe gradually gave way to a cosmos of stunning order and variety. As telescopes revealed more of these distant islands of stars, a pressing question emerged for astronomers. How could they possibly make sense of this cosmic menagerie? The man who provided the answer was Edwin Hubble. He devised an elegantly simple way to categorize galaxies, a system so intuitive it is still used today. He sorted them by their shapes into a sequence that resembles a tuning fork. On one prong of the fork are the spiral galaxies like our own Milky Way. These are the grand pinwheels of the cosmos, characterized by their flat, rotating disks and sweeping arms that coil out from a bright central bulge. They are often rich with the gas and dust needed to form new stars, making them vibrant and dynamic stellar nurseries. On the other prong sit the barred spirals, similar to their cousins, but with a distinct, straight bar of stars cutting through their center, with the spiral arms emerging from the ends of this bar. The handle of Hubble's tuning fork is home to the elliptical galaxies. These are the cosmic elders, appearing as smooth, featureless ovals or spheres. They lack the flat disk and spiral arms of their younger counterparts, and are composed mostly of older, redder stars with very little of the gas required to spark new stellar life. Their serene appearance, however, is deceptive. They are often the product of violent galactic mergers, the final, quiet state after a colossal cosmic collision. Finally, there are the irregular galaxies, the misfits that defy Hubble's neat classification. These are the chaotic, shapeless clouds of stars, often the result of gravitational disturbances or messy encounters with other galaxies. A galaxy's place on this sequence is not random. It is a visual history book telling the story of its life. A spiral's graceful structure speaks of a quiet, orderly evolution, while a giant elliptical reveals a dramatic past of cosmic violence and merger. This simple classification scheme gives us our first clue to understanding the life stories written in the shapes of the stars. Spiral galaxies are cosmic whirlpools, immense structures defined by their graceful, spinning disks. At the heart of a spiral like our Milky Way lies the central bulge, a dense, spherical swarm of primarily older, reddish stars. This bulge is the galaxy's ancient core, a relic from its earliest, more chaotic days of formation. But the most dynamic part of the galaxy is the vast, pancake-thin disk that extends outward from this central hub. This disk is where the action is. It is a bustling, rotating plane composed of billions of stars, along with enormous clouds of gas and dust. These components all travel in a remarkably orderly, circular dance around the galactic center, much like horses on a carousel. Our own Sun, for instance, completes one full orbit around the Milky Way center roughly every 230 million years. The spiral arms themselves are not permanent structures made of the same stars, but are instead like cosmic traffic jams, density waves that move through the disk. As gas and stars enter these waves, they compress, triggering the brilliant bursts of star formation that make the arms so luminous and easy to see. Encasing this entire brilliant structure is the galactic halo, a vast spherical cloud. This halo is home to isolated, ancient stars and the globular clusters that orbit the galaxy like distant bees around a hive. Most importantly, it is here that the true foundation of the galaxy resides, a massive sphere of invisible dark matter. Its immense gravitational pull is the only thing holding the entire spinning disk together, preventing its stars from flying off into the emptiness of intergalactic space. While spiral galaxies are vibrant with youthful star formation, elliptical galaxies represent the universe's quiet retirement communities. These cosmic elders are vast, smooth, and serene, appearing as immense football-shaped spheres of stars. They are almost entirely devoid of the gas and dust that fuels new stellar births, meaning their star-forming days are long behind them. The stars within an elliptical galaxy are predominantly old, cool, and red, having burned for billions of years. This gives these galaxies a uniform reddish-orange glow, a stark contrast to the brilliant blue pockets of young stars that illuminate a spiral's arms. Their serene appearance, however, belies a dramatic and violent origin story. Most giant elliptical galaxies are not born this way. They are forged in the colossal collisions and mergers of spiral galaxies. When two spirals are drawn together by gravity, their delicate structures are torn apart in a chaotic billion-year dance. Their stars, which are so widely spaced that they rarely collide, are instead flung into new, randomized orbits, creating the featureless spherical shape. Meanwhile, their vast reservoirs of gas and dust are violently compressed, triggering a final, ferocious burst of star formation known as a starburst. This explosion of new life quickly consumes the remaining fuel. Once this last gasp is over, with no gas left to form new stars, the merged galaxy settles into its final form, a calm and quiet elliptical. It becomes a cosmic retirement home where ancient stars orbit in a peaceful, collective glow, their dramatic history of creation and collision written only in their serene, final shape. This serene retirement, however, can be a deceptive mask for a galaxy's ongoing predatory nature. The cosmos operates on a simple, brutal principle: the strong consume the weak. Galactic cannibalism is a routine and violent process that fuels the growth of the largest galaxies. Imagine a giant elliptical galaxy, that calm sphere of ancient stars, sitting at the gravitational center of a vast group of smaller galaxies. Its immense pull acts as an inescapable trap. Over billions of years, smaller satellite galaxies, often dwarf irregulars or tiny spirals, are drawn into its clutches. They do not simply crash into the giant head-on. Instead, they are slowly torn apart by extreme tidal forces, the same kind of gravitational stretching that the Moon causes on Earth's oceans, but on a catastrophic scale. As a dwarf galaxy swings close, the difference in gravity between the side nearest the giant and the side farthest away is so immense that it stretches the smaller galaxy into long, brilliant streams of stars and gas. These stellar rivers, often visible to powerful telescopes as faint, arcing trails, are the ghostly remains of a galaxy being devoured. The stars themselves are siphoned away, joining the vast population of the predator, while any remaining gas is either consumed or stripped away into the void. This process does not just add stars, it fundamentally changes the cannibal. With each meal, the giant galaxy grows more massive and puffs up, its spherical shape reinforced by the random orbits of the newly acquired stars. Our own Milky Way is not innocent of this cosmic predation. We are currently in the act of consuming several smaller dwarf galaxies, and their stellar debris is scattered throughout our galactic halo, a silent testament to the fact that even beautiful spirals can be predators. Deep within the calm, ordered spin of a spiral galaxy, or hidden at the heart of a giant elliptical, lies a cosmic monster. Nearly every large galaxy we have observed harbors a supermassive black hole at its very center. Our own Milky Way is no exception. At its core, 27,000 light-years away, sits Sagittarius, a star, a gravitational behemoth with a mass 4 million times that of our Sun. These are not the black holes formed from a single collapsing star. These are entities of an entirely different scale, born in the earliest chaos of the universe and grown to staggering proportions over billions of years. For a long time, we thought of them as passive, invisible drains in space, simply consuming whatever stray gas or stars wandered too close, but we now know they are anything but passive. A supermassive black hole can become the ultimate galactic puppet master. When vast amounts of material are drawn into its accretion disk, a swirling, superheated whirlpool of doomed matter, the black hole does not swallow everything. Intense magnetic fields can funnel some of the infalling gas into powerful, focused jets that scream outward at nearly the speed of light. These jets pump colossal amounts of energy back into the surrounding galaxy. This energy can heat up the galactic gas, preventing it from cooling and collapsing to form new stars. In this way, a single black hole can effectively shut down star formation across an entire galaxy, putting a final cap on its growth and evolution. The relationship is a delicate and violent feedback loop. The galaxy feeds the black hole, and the black hole, in turn, dictates the future of the galaxy that hosts it. A galactic collision is the ultimate creative destruction. When two immense galaxies are drawn together by gravity, their dance is not one of pure annihilation. The spaces between stars are so vast that direct stellar impacts are incredibly rare. Instead, the real drama unfolds within the galaxy's immense reservoirs of gas and dust. As the galaxies begin their gravitational tango, their structures are violently distorted. Immense tidal forces, far greater than any ocean tide, sweep through these cosmic clouds. This chaotic interaction acts like a giant cosmic hand, violently squeezing these vast nebulae. The gas clouds are compressed to extreme densities, and in the world of star formation, compression is the ultimate trigger. This sudden, intense pressure ignites a ferocious firestorm of stellar birth, a phenomenon astronomers call a starburst. In a normal galaxy like our Milky Way, a handful of new stars are born each year. But during a starburst, that rate can explode into hundreds or even thousands of new stars annually. These are not the gentle, long-lived stars like our Sun. The starburst forges predominantly massive, brilliant blue stars that burn through their nuclear fuel in a mere few million years, dying in spectacular supernova explosions. For a brief, dazzling cosmic moment, a starburst galaxy can outshine all the other stars in the two merging galaxies combined, a brilliant but fleeting blaze of glory signaling a fundamental transformation. These brilliant, star-filled islands are not solitary wanderers in the cosmic ocean. Galaxies are profoundly social, gathering together in the largest structures that gravity can possibly bind. We call these immense gatherings galaxy clusters, and they represent the pinnacle of cosmic architecture. A single cluster can contain hundreds, sometimes even thousands, of individual galaxies, all held in a mutual gravitational embrace. Picture our own Milky Way. We are part of a smaller group called the Local Group, which includes our great spiral neighbor Andromeda and dozens of smaller dwarf galaxies. But this is just a tiny village. A true galaxy cluster is a sprawling metropolis. The Virgo cluster, the nearest major cluster to us, contains well over 1,000 member galaxies. Within these clusters, galaxies zip around at incredible speeds, their motion dictated by the cluster's immense total gravity. But here is the real mystery. When astronomers first measured the speeds of these galaxies, they found something astonishing. The individual galaxies were moving so fast that the gravity from all the visible stars and gas within the cluster should not have been nearly strong enough to hold the cluster together. The entire metropolis should have flown apart long ago. So what is providing the extra gravity, the cosmic glue that keeps these colossal structures bound together? The answer, once again, lies in the unseen. The true backbone of a galaxy cluster is not the galaxies themselves, but an immense, seething cloud of superheated gas and an even more massive halo of dark matter. This invisible framework holds the key to the universe's largest communities. But this cosmic glue, the dark matter holding clusters together, is not the final word on the universe's fate. A far more mysterious and dominant force is at work on the grandest stage of all. For much of the 20th century, astronomers believed the universe's expansion, the aftermath of the Big Bang, was gradually slowing down. They assumed the collective gravity of all matter was acting as a cosmic brake, gently pulling everything back together. Then, in the late 1990s, two independent teams of researchers made a discovery so shocking it earned them the Nobel Prize. By observing distant supernovae, they found that the expansion of the universe is not slowing down at all. It is speeding up. Galaxies and the vast clusters they call home are flying away from each other at an ever-increasing rate. Something is actively pushing the cosmos apart, overcoming the relentless pull of gravity itself. This mysterious something was named dark energy. We do not know what it is. We cannot see it or touch it, but its effects are undeniable. Current measurements suggest dark energy makes up a staggering 68% of the entire cosmos. It is the dominant component of the universe, with dark matter and all the visible stars and galaxies making up the remainder. Think of it as a kind of anti-gravity, an inherent property of empty space itself that generates a repulsive force. On the scale of our solar system or even our galaxy, its effect is negligible, completely overwhelmed by local gravity. But across the vast, empty voids between galaxy clusters where gravity is weak, its push becomes dominant. It is as if the very fabric of space-time is stretching itself apart from within. This discovery completely rewrote our understanding of cosmic evolution and unveiled the ultimate fate of the universe. A future where galaxies will recede from one another into an ever-deepening and lonely isolation. Our own cosmic home is on an unstoppable collision course. The Andromeda Galaxy, that faint smudge of light in our night sky, is not a distant neighbor. It is a massive spiral hurtling directly towards us at an astonishing speed of over 250,000 miles per hour. In roughly 4 billion years, our two galaxies will meet. From our perspective on Earth, the approach will be a slow-motion spectacle spanning millions of years. Andromeda will grow from a faint blur into a magnificent, sprawling pinwheel that eventually fills the entire heavens. As the galaxies begin their first close pass, their mutual gravity will warp and tear their structures apart. long, brilliant streams of stars will be flung into the darkness, and the familiar band of the Milky Way will be twisted into a chaotic, unrecognizable tapestry of light. Do not imagine a cataclysm of exploding stars, however. The vast distances between stars mean our solar system will almost certainly be unharmed, flung into a new orbit within the emerging hybrid galaxy. After this first dramatic encounter, the two galaxies will swing apart, only to be pulled back together for a final merger. Over another billion years, they will settle into a single, enormous elliptical galaxy, which astronomers have already named Milcomda. This new galaxy will be a tranquil sphere of ancient stars, its violent history of creation written in the serene, final glow of its combined light. The serene glow of a giant elliptical galaxy is a cosmic fossil, preserving a story that spans billions of years. The galaxies we observe today, in all their varied forms, are not static portraits. They are single frames in a movie that has been playing for over 13 billion years. Every spiral, every ellipse, every irregular cloud of stars is the current result of an epic narrative of continuous change. This evolution is not something we can watch in real time, as a human lifetime is but a blink compared to the lifespan of a galaxy. Instead, we piece together this history by looking out into space, which is also looking back in time. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago. By comparing these ancient galaxies to the ones in our cosmic neighborhood, we can trace their life stories. We see that the earliest galaxies were small, chaotic, and rich with gas, furiously forming their first generations of stars. Over eons, they grew through mergers and acquisitions, their shapes morphing from irregular clumps into majestic spirals, or being reshaped entirely into smooth ellipticals through colossal collisions. The very elements that make up our world, the iron in our blood and the calcium in our bones, were forged inside stars and scattered by supernova across these vast timescales, slowly enriching the galactic gas with the heavy elements needed for planets and life. The galaxy you see in a telescope tonight is not a finished product, but a temporary state in an ongoing saga of transformation that is far from over. Even the most fertile galactic nurseries can be sterilized by their own internal violence. A galaxy's lifeblood is its cold gas, the raw material for new stars. But this vital resource can be violently stripped away by galactic winds, powerful outflows generated from within the galaxy itself. These are not gentle breezes, but hurricanes of superheated gas racing outward at millions of miles per hour. Their source is twofold. First, the cumulative fury of countless supernova explosions from short-lived, massive stars can create a collective shockwave, blowing vast bubbles of hot gas that drive the surrounding cold gas clean out of the galaxy. Second, and even more potent, are the winds driven by an active supermassive black hole at the galaxy's core. When a black hole is feasting, the intense radiation and colossal pressure from its accretion disk can launch titanic winds that sweep through the entire galactic disk. Imagine a giant cosmic leaf blower powered by a gravitational monster scouring a galaxy of its star-forming fuel. This process, known as quenching, effectively shuts down a galaxy's star formation. The galaxy does not die instantly, but its future is sealed. It enters a long, slow decline, its stellar population aging without renewal, its blue spiral arms fading to the quiet red of old stars. This dramatic feedback loop reveals a profound truth. A galaxy's most energetic events contain the seeds of their own eventual stillness. This stretching of light is our most powerful tool for mapping cosmic history. When we observe a distant galaxy, its light is not arriving in its original form. The expansion of the universe itself acts upon that light during its long journey across the void. As space stretches, the light waves traveling through it are stretched along with it. This phenomenon is called redshift because it shifts the light towards the red end of the electromagnetic spectrum. Imagine the sound of a passing ambulance siren. As it moves away from you, the sound waves are stretched, lowering the pitch. Redshift is the visual equivalent of that Doppler effect, but on a cosmic scale. The greater the distance to a galaxy, the more space has expanded during the light's travel time, and the more extreme its redshift becomes. This is not just a visual quirk, it is a direct measurement of cosmic expansion. By analyzing the redshift of a galaxy, astronomers can calculate not only its distance but also how long its light has been traveling to reach us. When we point our most powerful telescopes at a galaxy with an immense redshift, we are not just looking across space, we are peering back into time. We are seeing that galaxy as it was when the universe was young, a fossilized snapshot of its ancient past. This is how we witness the earliest epochs of galaxy formation, observing infant galaxies not as they are today, but as they were billions of years ago, their light finally arriving after a journey across an ever-widening gulf. For all their grandeur, the majestic spirals and giant ellipticals are cosmic aristocrats, vastly outnumbered by a silent majority. The most common type of galaxy in the universe is not a sprawling pinwheel but a faint, diminutive dwarf. These cosmic minnows are everywhere, swarming around larger galaxies like our own Milky Way in vast, faint halos. They contain only a few billion stars, a mere pittance compared to the hundreds of billions in a galaxy like Andromeda. Their faint glow makes them incredibly difficult to detect, hiding in the shadows of their brighter, more famous cousins. Yet their sheer abundance tells us something profound about the process of cosmic construction. Astronomers now believe these dwarfs are the primordial building blocks of the universe. In the early cosmos, the first structures to form were not the grand galaxies we see today, but countless small, clumpy protogalaxies similar to modern dwarfs. Over billions of years, gravity drew these tiny islands together. They merged, collided, and coalesced, their stars and dark matter slowly assembling into the larger, more complex structures we now recognize as spirals and ellipticals. Our own Milky Way is a living testament to this process. It did not form in isolation, but grew by consuming dozens, perhaps even hundreds, of these smaller dwarfs over its long history. Their stellar debris still orbits within our galactic halo, the scattered remains of the very blocks that built our cosmic home. So when you look up at the grand band of the Milky Way, remember that its majestic sweep is the final product of a billion-year construction project, assembled from the faint, forgotten glow of the universe's most common inhabitants. Just as planets have a sweet spot for life, so too do entire galaxies. The concept of a galactic habitable zone proposes that not every corner of a galaxy is equally suited for nurturing complex life. This is not about a single star's warmth, but about a region's entire cosmic environment, balancing the necessities of chemistry against the perils of astrophysics. The first requirement is a rich supply of heavy elements, the very building blocks of rocky planets and organic molecules. These elements, like carbon, oxygen, and iron, are forged in the hearts of stars and scattered by their explosive deaths. They are not evenly distributed throughout a galaxy. In the dense, crowded core, stellar generations have lived and died in rapid succession, enriching the gas with these vital ingredients. But the galactic center is also a profoundly dangerous neighborhood. It is packed with stars, increasing the risk of a nearby supernova whose radiation could sterilize nearby planets. Even more threatening is the supermassive black hole at the very heart, whose occasional violent outbursts can flood the inner galaxy with lethal radiation. Farther out, in the sparse, quiet outskirts of the galactic disk, the threat of catastrophe diminishes. Yet here, the problem is poverty, not peril. The galactic suburbs have not seen enough stellar cycles to build up a significant abundance of heavy elements. Planetary systems forming in these remote regions might lack the necessary raw materials for a rocky, life-bearing world like Earth. The galactic habitable zone is therefore a narrow, golden ring, a circumstellar belt located between the chaotic, metal-rich core and the barren, metal-poor frontier. It is a region where a solar system can inherit just the right amount of stellar debris to form terrestrial planets. while remaining at a safe enough distance from the galaxy's most violent events. Our own solar system orbits within this privileged zone, about halfway out from the Milky Way center, a fortunate location in a vast and often unforgiving cosmos. The graceful arms of a spiral galaxy are cosmic illusions, brilliant but temporary patterns in a rotating sea of stars. These sweeping structures are not rigid, physical formations like the arms of a pinwheel. If they were, the galaxy's rotation would wind them up tightly, destroying their beautiful shape within a few 100 million years. The solution to this puzzle lies in a concept called a density wave. Think of a spiral arm not as a thing, but as a process, a celestial traffic jam moving through the galactic disk. Just as cars slow down and bunch up when they approach a construction zone on a highway, stars and vast clouds of gas slow their orbit and compress as they enter a spiral arm. The stars, which are already shining, simply pass through this crowded region, appearing brighter and more numerous for a time before moving out the other side. The real magic happens with the gas. These immense molecular clouds are squeezed to incredible densities by the wave's passage. This violent compression is the ultimate trigger for star birth, forcing pockets of gas to collapse under their own gravity. As a result, the spiral arms become lined with brilliant blue newborn stars and glowing pink nebulae, like streetlights illuminating a cosmic boulevard. These massive young stars are so luminous that they define the arm's visible outline. Even though they are just temporary residents, they are born, shine brilliantly for a few million years, and often explode as supernova before they even have a chance to leave the traffic jam that created them. The spiral arm we see is therefore a continuous wave of creation, a self-perpetuating pattern of birth and light that moves through the galaxy, forever shaping its luminous, evolving portrait. This accelerating expansion we observe today, however, is a relatively new chapter in the cosmic story. For much of the universe's history, the script was written by a different force entirely. In the beginning, gravity was the undisputed ruler of cosmic expansion. The universe was far smaller and immensely denser, with all its matter and energy packed into a much tighter space. This concentration meant that gravity's collective pull, the mutual attraction of every galaxy, star, and particle for every other, was overwhelmingly powerful. For billions of years, this relentless gravitational tug of war acted as a cosmic brake, steadily slowing down the rate of the universe's expansion following the Big Bang. Imagine rolling a ball up a very steep hill with gravity constantly pulling it back, sapping its speed. The early universe was in a similar state, its initial explosive momentum being steadily eroded by the collective pull of all the matter within it. We can actually observe this decelerating past by looking at the light from the most distant, ancient supernova. Their redshift tells a story not of acceleration, but of a cosmos gradually applying the brakes. This was the universe's long childhood, a period where gravity's unifying embrace was the dominant influence on its ultimate fate. Then something changed. As the universe continued to expand, it also grew more diffuse. The average distance between galaxies increased and gravity's grip, which weakens with distance, began to fade. It was at this point, around 5 billion years ago, that the balance of power dramatically shifted. The repulsive push of dark energy, a constant force inherent to space itself, finally overcame the ever-weakening pull of gravity. The cosmic brakes were released, and the universe began to speed up, entering the era of accelerated expansion we now inhabit. This transition from deceleration to acceleration marks one of the most profound turning points in cosmic history, a moment when the universe's destiny was rewritten by an invisible energy we are still struggling to understand. The color of a galaxy is its autobiography written in starlight. Young galaxies blaze with a brilliant, energetic blue. This vibrant hue does not come from the galaxy itself, but from its most luminous and short-lived residents, massive O and B-type stars. These are the stellar titans born in the dense, cold clouds of a galaxy's star-forming regions. They burn ferociously hot and bright, emitting most of their light in the blue and ultraviolet parts of the spectrum. Because they are so massive, they race through their nuclear fuel in just a few million years, a mere blink in cosmic time. Their brilliant blue light, therefore, is a sure sign of a galaxy's youth and vitality, a declaration that it is still actively building, still giving birth to new generations of stars. But this blue phase cannot last forever. As a galaxy ages, its story shifts. The most massive blue stars quickly exhaust their fuel and die in spectacular supernova. What remains is a population of smaller, more frugal stars like our own Sun, and the countless red dwarfs that can burn for trillions of years. These stars are cooler and emit their light predominantly in the red part of the spectrum. If a galaxy continues to form new stars, the brilliant blue light from its nurseries can mask this underlying red population. However, once its gas supply is depleted or stripped away, the star formation stops. The last of the blue giants flicker out, and there are no new ones to replace them. Without that brilliant blue light to dominate, the galaxy's collective color shifts. It fades from a vibrant blue-white to a yellow, and finally settles into the steady, red glow of its long-lived stellar majority. This transition from blue to red is one of the most fundamental markers of a galaxy's life cycle, a visual record of its passage from a turbulent, star-forming youth to a quiet, aging maturity. These spectacular bridges and tails are the visible scars of a gravitational war. When two galaxies draw near, their mutual pull creates immense tidal forces, a difference in gravity so extreme it can stretch a world. But here, the world being stretched is an entire galaxy. The side of a galaxy closest to its partner feels a much stronger tug than the side farther away. This gravitational differential pulls the galaxy apart, drawing out vast rivers of stars, gas, and dust. These are not explosions, but a slow, majestic unraveling. The result is a breathtaking celestial spectacle, with long, luminous tails often arcing far away from the merging pair, while delicate bridges of material stretch between them, connecting the two in a final, beautiful embrace before their eventual union. These structures can be immense, stretching for hundreds of thousands of light years, sometimes even longer than the original galaxies themselves. They are ephemeral, lasting only a few 100 million years before the stars within them disperse or fall back into the newly merged galaxy. The most famous example is the Mice galaxies, a pair of colliding spirals located about 300 million light-years away. Through our telescopes, we see two distinct galactic cores, each trailing long, sweeping tails of stars that look like the streaming bodies of two celestial mice. This is not a static picture, it is a snapshot of an ongoing disaster, a dance of destruction and creation happening in slow motion. Within these drawn-out tails, the violent compression of gas clouds can ignite their own bursts of new star formation, lining the cosmic wreckage with brilliant blue clusters. It is a poignant reminder that even in the throes of destruction, the universe finds a way to create new light. Our own Milky Way does not drift through the cosmos in solitary splendor. It is part of a small, gravitationally bound family we call the local group, a collection of over 50 galaxies all dancing to the same silent tune of mutual attraction. This is our immediate galactic neighborhood, a region of space about 10 million light-years across. The dominant members of this family are three great spiral galaxies, the Milky Way, the Andromeda Galaxy, and the smaller, beautiful Triangulum Galaxy. The rest of the local group's population is made up of dozens of dwarf galaxies, tiny cosmic minnows that orbit these three larger giants like moons around a planet. This entire collection is an isolated island in the grander cosmic ocean, falling together through its own shared gravity, completely separate from the immense metropolitan clusters that lie beyond. Within this local community, we can witness the full life cycle of galaxies, from the primal building blocks represented by the dwarfs to the majestic spirals in their prime. and even see the future merger that will create a new hybrid galaxy. The local group is our cosmic backyard, a laboratory where we can study the intimate dynamics of how galaxies live and interact on the smallest of cosmic scales. The silent, ancient stars scattered throughout our galactic halo are history books written in gravity and chemistry. We cannot rewind time to watch the Milky Way form, but we can uncover its violent childhood by reading these stellar fossils, a field known as galactic archaeology. It begins with a simple but profound idea. Stars that formed together in the same primordial cloud or dwarf galaxy share a common origin. They move through space on similar paths and are composed of the same unique blend of elements, a chemical fingerprint. When a small galaxy is consumed by the Milky Way, gravity shreds it, scattering its stars across our halo. But these stars do not forget their birthplace. They continue to travel in vast, coherent streams, like a school of fish released into an ocean, all moving in the same direction. By mapping the positions and, more importantly, the precise motions of millions of individual stars, astronomers can identify these ghostly rivers of stars flowing around us. They can then trace these streams backward, like following a celestial breadcrumb trail, to reconstruct the size, trajectory, and even the timing of the ancient collision that brought them here. The chemical composition of these stars adds another layer to the story. Stars from a small, primitive dwarf galaxy will have a much lower abundance of heavy elements like iron compared to stars born in the richer, more mature Milky Way. By analyzing a star's light, its spectrum, we can read this chemical signature. When we find a group of stars all moving together on a strange, looping orbit and all sharing the same primitive chemistry, it is a smoking gun. We have identified the remains of a long-dead galaxy, a building block that helped construct our cosmic home. Our Milky Way's serene disk is therefore an illusion of the present, masking a dramatic past of relentless cannibalism written in the motions of its oldest stars. This deep, pervasive redness is the final chapter for many of the universe's largest galaxies. Astronomers have a stark, simple name for these colossal systems: red and dead. A red and dead galaxy is a cosmic ghost town, a place where the vibrant cycle of stellar birth has ceased entirely. These are almost always the giant elliptical galaxies we see at the hearts of dense clusters, the gravitational bullies that have dominated their surroundings. Their red color comes from their stellar population, a uniform sea of ancient, long-lived stars that are cool and emit their light in the red part of the spectrum. The dead part of the name is even more telling. It means they have completely exhausted their supply of cold, dense gas, the raw material required to form new stars. Without this fuel, the galaxy's stellar population simply ages in place. The brilliant, short-lived blue stars that once lit up its youthful years have all flared out, leaving behind a quiet, red glow that will slowly, imperceptibly dim over trillions of years. How does such a massive galaxy run out of fuel? The mechanisms are brutal. In the crowded environment of a galaxy cluster, the space between galaxies is not entirely empty. It is filled with a superheated, thin gas. As a galaxy moves through this intergalactic medium at millions of miles per hour, this hot gas acts like a powerful cosmic wind, physically stripping away the galaxy's own cool gas reservoir in a process called ram pressure stripping. It is like driving a car through a heavy downpour where the rain strips leaves from the trees. At the same time, internal processes seal its fate. The combined fury of countless supernovae and the violent outbursts from its central supermassive black hole blow away or heat up any remaining gas, preventing it from ever cooling down to form new stars. The galaxy is effectively quenched, its evolution brought to a permanent standstill. It becomes a fossil, a monument to a violent and active past, now frozen in a state of serene, red retirement. This cosmic architecture extends far beyond our local group into the largest structures imaginable. If you could pull the camera back to view the entire observable universe, you would not see a random scattering of galaxies. Instead, you would witness a breathtaking pattern, a vast cosmic web stretching across the emptiness. This web is composed of immense, thread-like filaments of dark matter, each 100s of millions of light years long. These filaments intersect at dense nodes like glittering metropolises where thousands of galaxies swarm in massive clusters. And between these brilliant strands lie the cosmic voids, unimaginably vast regions of near-total emptiness, so large that our entire local group would be just a tiny speck inside one. This is the true large-scale structure of our cosmos, a sponge-like or web-like architecture that defines where galaxies can and cannot live. Every galaxy, from the brightest spiral to the faintest dwarf, is part of this grand design, strung along the luminous filaments or gathered at the crowded intersections. The voids, meanwhile, are the cosmic deserts. They are not completely empty, but they contain only a handful of isolated, lonely galaxies drifting in the darkness. This entire structure, this cosmic web, is the final magnified imprint of those first quantum ripples from the dawn of time, grown to a scale so immense it defies human comprehension. The universe is not a random collection of islands, but a single, interconnected tapestry of matter and emptiness, woven together by the invisible threads of dark matter. An active galactic nucleus is one of the universe's most violent and brilliant phenomena. At the heart of certain galaxies, the central supermassive black hole transforms from a quiet giant into a raging cosmic engine. This happens when a tremendous amount of gas, dust, and even entire stars are funneled into the black hole's accretion disk. This disk is a maelstrom of superheated matter, a whirlpool spiraling inward at near light speed. As the material rubs together under unimaginable friction and gravitational pressure, it heats up to millions of degrees, glowing with an intense, blazing light across the entire electromagnetic spectrum. The energy released in this process is so colossal that the tiny central region can outshine the combined light of every single star in its host galaxy. It becomes a lighthouse beam cutting across the cosmic dark, visible from billions of light years away. But the true power of an active galactic nucleus is not just in the light it emits. Some of these systems channel the chaotic energy into twin jets of charged particles that scream outward from the black hole's poles at nearly the speed of light. These jets can stretch for millions of light years into intergalactic space, punching through the galaxy and beyond, delivering vast amounts of energy into the cosmic voids. This incredible display, however, is a temporary phase in a galaxy's life, a brilliant but fleeting outburst that reveals the awesome power latent within the silent hearts of most galaxies. The universe builds its grandest structures from the smallest of beginnings. For decades, astronomers debated two competing visions for how galaxies came to be. One theory, known as top-down, suggested that vast, pancake-like clouds of gas collapsed first, fragmenting afterwards into individual galaxies. In this model, the largest structures define the cosmic landscape from the very start. The opposing view, the bottom-up model, argued the reverse. It proposed that tiny clumps of stars and dark matter, similar to modern dwarf galaxies, formed first. These primordial building blocks then spent billions of years merging, colliding, and coalescing, gradually assembling the majestic spirals and giant ellipticals we see today. Modern observations have delivered a clear verdict: the universe is a builder that works from the bottom up. This hierarchical model of formation is written in the very fabric of our cosmos. We see its evidence in the swarms of dwarf galaxies that orbit larger ones, the fossil streams of stars in our halo, and the ancient red cores of massive galaxies that reveal their long history of violent assimilation. Every large galaxy is a cosmic metropolis, its current grandeur the direct result of a billion-year construction project that started with the smallest of stones. Woven invisibly through the vast spaces between the stars, another force exerts its subtle influence. Galactic magnetic fields are a pervasive but often forgotten component of a galaxy's anatomy. These are not the simple fields of a bar magnet, but a complex, dynamic web of energy that threads its way through the entire interstellar medium, the thin soup of gas and dust that fills a galaxy's disk. This magnetic tapestry is incredibly weak, millions of times fainter than a common refrigerator magnet, yet it stretches across tens of thousands of light years. Its origins are a cosmic mystery, likely seeded by the earliest stars, and then stretched and amplified by the slow, churning motions of the galaxy itself. So what does such a faint field actually do? Its effects are surprisingly profound. These magnetic lines act like cosmic guardrails for some of the universe's most energetic particles, the cosmic rays that scream across the galaxy at nearly the speed of light. The field channels these particles, preventing them from simply flying off into intergalactic space and instead trapping them within the galactic disk, creating a persistent fog of high-energy radiation. More directly, these fields influence the very birth of stars. Within a giant molecular cloud on the verge of collapse, the magnetic pressure provides a supporting force that fights back against gravity's relentless pull. It can slow down the collapse of a cloud, regulating the pace of star formation and potentially influencing the final sizes of the newborn stars. While gravity is the master architect of galaxies, these invisible magnetic fields are the subtle sculptors, fine-tuning the grand processes of cosmic creation. Sometimes the most profound discoveries come from looking at nothing. Astronomers made a monumental decision with the Hubble Space Telescope to point its powerful lens at a patch of sky that was, by all previous accounts, completely and utterly empty. It was a tiny, dark void, a fraction the size of the full moon, seemingly devoid of any stars or galaxies. For 10 consecutive days in 1995, Hubble gathered every precious photon of light that arrived from this cosmic blackness. The resulting image, known as the Hubble Deep Field, did not reveal an empty void. It revealed a universe teeming with light. That single, small window into the darkness was filled with a breathtaking tapestry of nearly 3,000 galaxies, each one a distinct island of stars. There were majestic spirals, fiery ellipticals, and strange, misshapen blobs of light that represented galaxies under construction in the early universe. This was not just a beautiful picture, it was a radical census of the cosmos. It proved with undeniable clarity that the universe is uniformly filled with galaxies as far as our telescopes can see. If such a tiny, random speck of sky contains thousands of galaxies, then the entirety of the observable universe must contain an almost unimaginable number, a figure we now estimate to be in the hundreds of billions. The Hubble Deep Field transformed our perspective, shrinking the vast emptiness of space into a canvas overflowing with cosmic stories. Each tiny smudge of light, a galaxy with its own history of birth, life, and eventual transformation. For a galaxy, its cold gas reservoir is its future. This delicate, swirling mist of hydrogen is the very stuff from which new stars are born, the lifeblood of cosmic evolution. But this vital resource can be stolen in an instant on the cosmic timescale. One of the most dramatic and effective thieves is the environment of a galaxy cluster itself. Within these immense metropolises, the space between galaxies is not a perfect vacuum. It is filled with a thin, superheated gas known as the intracluster medium. This gas is so incredibly hot that it glows in X-rays, a seething, invisible fog that permeates the entire cluster. Now imagine a spiral galaxy, rich with cold gas, falling into this cluster for the first time. It plows through this intracluster medium at speeds of millions of miles per hour. The effect is like sticking your hand out of a car window at high speed, feeling the immense pressure of the wind. For the galaxy, this is not a gentle breeze but a hurricane-force gale. The pressure from this hot, thin gas is so powerful that it acts like a cosmic squeegee, physically scraping and stripping the cold gas right out of the galactic disk. This process has a precise name, ram pressure stripping. The galaxy's stars, bound tightly by gravity, are largely unaffected, but its tenuous gas, which is much more loosely held, is violently swept away, trailing behind the galaxy like the tail of a comet. In a relatively short time, the galaxy is left gasping, its star-forming fuel ripped away into the void. The result is a rapid and brutal transformation. A galaxy that was once a vibrant, blue, star-forming spiral can be quickly quenched, its star formation shut down almost overnight in cosmic terms. It begins to redden and fade, its destiny as a star-making factory abruptly and violently cut short by the simple act of moving through a crowded neighborhood. These faint, ghostly companions to our Milky Way tell a story of gravitational dominance and resilience. Our galaxy is not a solitary island, but the center of its own miniature cosmos, orbited by dozens of smaller dwarf galaxies. The most famous of these are the large and small Magellanic Clouds, visible as fuzzy patches in the southern hemisphere's night sky. These are not true spheres, but irregular, misshapen clouds of stars, gas, and dust. Their very forms are a testament to the Milky Way's immense gravitational influence. Each time they swing close on their long, looping orbits, our galaxy's tidal pull tugs at them, stretching their shapes and stirring up their internal gas. This gravitational harassment triggers bursts of star formation within them, creating brilliant blue clusters that stand out against their otherwise chaotic structures. Yet this relationship has a darker side. As the Magellanic Clouds travel through the halo of hot gas that surrounds our Milky Way, they are experiencing their own form of ram pressure stripping. The smaller cloud is particularly vulnerable, having lost a significant portion of its gas to this cosmic wind, a trail of its stolen future streaming behind it in a faint, gaseous ribbon. These satellite galaxies are living experiments, showing us in real time how a giant galaxy sculpts and eventually consumes its smaller neighbors. Their distorted forms a preview of their ultimate fate as they are slowly digested into the Milky Way's vast halo. A galaxy's rotation holds a secret that upended our understanding of the cosmos. As astronomers mapped the speeds of stars within spiral galaxies like our own, they expected to find a clear and logical pattern. The visible mass of a galaxy, all its stars and glowing gas, is concentrated in the bright central bulge and the inner disk. According to the laws of gravity established by Newton and refined by Einstein, stars farther from this central mass should orbit more slowly, just as Pluto moves at a more leisurely pace around the Sun than the inner planets do. This is simple orbital mechanics, but the observations revealed something astonishingly different. When they measured the orbital velocities of stars in the outer reaches of spiral galaxies, they found these distant stars were moving just as fast as those closer in. The rotation curve, a graph of orbital speed versus distance from the center, did not fall away as predicted. Instead, it remained flat all the way out to the galaxy's faintest edges. This was not just a small discrepancy, it was a fundamental failure of prediction. The only possible explanation was that there was far more mass in the galaxy than we could see. This mass had to be distributed in a vast spherical halo that extended far beyond the visible edge of the galactic disk, gravitationally tugging on those outer stars and whipping them around at impossible speeds. The stars themselves were telling us that most of the galaxy was made of something invisible, something that neither emitted nor absorbed light. This was the first direct and undeniable evidence that dark matter was not just a theoretical idea, but the dominant architectural material of the universe. The central bulge of a galaxy is its personal memoir written in starlight. Not all bulges are the same, and their subtle differences reveal dramatic chapters of cosmic history. Some galaxies, especially the majestic spirals, possess a classical bulge. This is a dense, spherical swarm of ancient stars orbiting the galactic center in a chaotic, random jumble, much like a buzzing swarm of bees. This kind of structure is a telltale sign of a violent past, a relic from an era when the young galaxy experienced a dramatic merger. When two smaller protogalaxies smashed together in the early universe, their stars were flung into disordered orbits, piling up at the center to form this dense classical hub. It is a fossil of a long-ago collision. Other galaxies, however, display a different kind of central structure known as a pseudobulge. This is not a sphere, but a flattened, disk-like concentration that often contains a miniature spiral pattern or a distinct bar of its own. Unlike the chaotic classical bulge, a pseudobulge forms quietly and gradually from the galaxy's own rotating disk. Over eons, the galaxy's spiral arms or central bar can funnel gas inward, where it settles and slowly builds up this disk-like, ordered structure through a steady, internal process of star formation. So the next time you see an image of a spiral galaxy, look closely at its bright heart. Is it a round, classical bulge whispering of an ancient cosmic crash? Or is it a disguised pseudobulge, the product of a more serene and orderly evolution? That central glow holds the answer, a single clue that can unravel billions of years of a galaxy's life story. This cosmic dawn was not a gentle sunrise, but a violent, transformative storm. For hundreds of millions of years after the first stars flickered on, the universe remained shrouded in a thick, opaque fog of neutral hydrogen gas. Light could not travel far, trapped and scattered by this pervasive cosmic mist. The space between the first protogalaxies was a dark, impenetrable murk. Then a revolution began. The earliest galaxies and quasars, those brilliant beacons powered by voracious black holes, started flooding the cosmos with an intense, unprecedented torrent of ultraviolet radiation. This was not the gentle light of a single star, but a collective, searing glare from countless stellar nurseries and active nuclei. This energetic ultraviolet light began to strike the neutral hydrogen atoms that filled all of space. Each photon carried enough power to knock the electron clean off a hydrogen atom, tearing the atom apart and turning it into a free-floating proton and electron. This process, known as ionization, began to carve out transparent bubbles in the opaque fog. Imagine a dense, dark forest where someone starts lighting powerful torches. Around each flame, the darkness retreats, creating a clearing of light. In the cosmos, each of the first galaxies became such a torch. Its radiation created a growing, transparent bubble of ionized hydrogen in the surrounding fog. Over several 100 million years, these individual bubbles grew larger and began to overlap, their edges merging as more and more galaxies ignited. The universe was undergoing a fundamental phase change, a cosmic-scale clearing of the air. This was the epoch of reionization, the moment the cosmic fog lifted for good. By the time this era concluded, roughly 1 billion years after the Big Bang, the neutral hydrogen fog had been entirely burned away. The universe was left transparent, a dark and clear expanse through which light could now travel for billions of years without obstruction, finally opening the cosmic stage for the grand theater of galaxies we observe today. Some of the universe's most striking structures are born from a perfect cosmic robbery. Picture a majestic spiral galaxy, its disk spinning serenely in the darkness. Now imagine a smaller, gas-rich companion galaxy daring to swing too close on a perpendicular orbit, passing directly over the larger galaxy's poles. The smaller galaxy does not survive the encounter. It is completely torn apart by the giant's gravity, but its precious cargo of gas and stars is not simply consumed. Instead, this captured material is strung out into a brilliant, luminous ring that continues to orbit at a right angle to the main galactic disk, encircling it like a celestial hula hoop. This is a polar ring galaxy, a rare and spectacular configuration that looks more like a piece of celestial jewelry than a random collection of stars. The ring itself is a dynamic structure, a vast rotating belt of gas, dust, and newborn stars that orbits over the galactic poles, tracing a path that seems to defy the logic of a typical spiral. These rings are not permanent, though. Over hundreds of millions of years, the ring will gradually wobble and disperse, its material eventually settling into the main disk of the host galaxy. But for a cosmic moment, we are given a perfect snapshot of a gravitational theft frozen in time, a visible record of a smaller galaxy's sacrifice that decorated a giant with a crown of stolen light. This shift in a galaxy's color is a direct measure of its life being extinguished. We can actually witness this cosmic quenching on a grand scale through a phenomenon known as the Butcher-Ohmler effect. In the 1970s, astronomers Harvey Butcher and Augustus Ohmler made a startling discovery while studying distant galaxy clusters. They found that these clusters, when viewed as they were billions of years ago, looked dramatically different from the clusters we see in our modern universe. Instead of being dominated by the serene, red glow of old elliptical galaxies, these ancient clusters were teeming with vibrant blue star-forming spirals. It was as if the galaxy clusters of the past were bustling, youthful cities, while their modern counterparts are quiet retirement communities. This observation was profound because it revealed that the environment of a dense cluster actively and rapidly changes the galaxies within it. A spiral galaxy falling into a cluster does not get to keep its star-forming ways for long. The violent processes of ram pressure stripping, tidal interactions, and galaxy harassment work together to efficiently rob it of its gas, its lifeblood. The Butcher-Ohmler effect captures this universal transition, a clear before and after picture that shows us galaxy evolution in action. It demonstrates that a galaxy's destiny is not written solely at its birth, but is profoundly shaped by the company it keeps, a story of vibrant blue fading to a permanent and quiet red. The violent death of a massive star is not merely an end, it is a beginning. When a supernova explodes, it does more than just scatter newly forged elements across the galaxy. The unimaginable force of the blast can launch huge plumes of hot gas clear out of the galactic disk, hurling them high above and below the plane of stars. This superheated material, rich with iron, oxygen, and carbon, rises into the galactic halo like a colossal geyser. For a time, it drifts in the darkness, a vast cloud of incandescent vapor. But the galaxy's gravity is relentless. As this ejected gas radiates its heat away into the void, it slowly cools and condenses. Eventually, it can no longer resist the pull of the galaxy below. In a breathtaking cosmic rain, the cooled gas falls back down, splashing onto the galactic disk in massive, dense clumps. Astronomers call this cyclical process a galactic fountain. It is a vital form of cosmic recycling. This returning material is not the pristine hydrogen and helium from which the first stars were born. It is heavily enriched with the very elements that were forged in the star's core and during its violent death. When this metal-rich gas falls back into the spiral arms, it becomes the raw material for a new generation of stars and planets. Our own solar system was likely built from such recycled debris, the remnants of countless stellar explosions that once fountained high above the Milky Way, carrying within them the seeds of worlds and life itself. Some galaxies are cosmic phantoms, so faint they nearly vanish against the blackness of space. Ultra-diffuse galaxies are a profound puzzle, spanning the same vast distances as our own Milky Way, yet containing only 1% of its stars. Imagine a ghostly, translucent imprint of a grand spiral, its starlight so sparse you could see straight through its heart. Detecting these spectral giants is a monumental challenge, requiring the most sensitive telescopes to pick up their faint glow from the sea of darkness. Their existence raises a fascinating question. How can something so large contain so little? The leading theory suggests these galaxies were born in unusually quiet environments, perhaps in cosmic voids where they were starved of the gas needed to build many stars. Another possibility is that they suffered an early and violent history, where intense supernova winds or the activity of a central black hole blew away their star-forming fuel before they could fully mature. Their dark matter halos, however, must be immense to hold such a spread-out structure together against the pull of other galaxies. These faint giants are a reminder that the universe still holds profound mysteries, and sometimes the most intriguing stories are written in the faintest possible light. Our deepest views into the past are now being delivered by an eye in the void. The James Webb Space Telescope is more than a powerful observatory. It is a functioning time machine. Its primary mission is to gaze backward to capture the faint, stretched light from the universe's infancy. This is possible because of its incredible sensitivity to infrared light. As the universe expands, the light from the most ancient galaxies is stretched on its long journey to us, shifting from visible wavelengths into the infrared part of the spectrum. For previous telescopes like Hubble, this light was too red and too faint to detect, but Webb is designed specifically to see this cosmic redshift. It operates in the deep cold of space, its instruments chilled to suppress their own heat, allowing it to perceive the whisper of warmth from the first starlight. Every image it takes is a portal to a different era. When Webb stares at a patch of sky for days, it is not just collecting photons, it is gathering ancient stories. It has already spotted galaxies that existed when the universe was only a few 100 million years old. Cosmic infants that should not, by our old models, have grown so large so quickly. These primordial smudges of light are revolutionizing our understanding of cosmic dawn, revealing a universe that got its act together with astonishing speed, building complex structures far earlier than anyone had dared to predict. Each new observation from this time machine is rewriting the first chapters of our cosmic history. A galaxy's destiny is largely sealed by its birth weight. The initial mass a galaxy gathers acts as a cosmic bank account, dictating its ability to attract and retain the resources needed for a long and productive life. This fundamental link between mass and fate is powerfully illustrated by the mass-metallicity relation, a clear trend observed across the universe. Simply put, more massive galaxies contain a greater proportion of heavy elements, everything heavier than hydrogen and helium. These elements, which astronomers call metals, are the building blocks of rocky planets, complex molecules, and life itself. So how does this relationship come to be? It begins with gravity's relentless pull. A more massive galaxy, anchored by a stronger gravitational well, is far better at holding onto the precious gas it collects. It can also draw in more gas from its surroundings and from the smaller galaxies it consumes. This abundant fuel allows for continuous, vigorous star formation across billions of years. Each generation of stars fuses hydrogen and helium into heavier elements in their cores, and when the most massive ones explode as supernova, they seed the galactic gas with these newly forged metals. In a massive galaxy, this enriched gas is rarely lost. It remains trapped by the powerful gravity, ready to be recycled into the next round of star and planet formation. With each cycle, the galaxy's gas becomes richer and richer in metals, elevating its overall chemical abundance. A smaller, lighter galaxy faces a much harsher reality. Its weak gravitational grip is easily overcome. The fierce radiation from its own newborn stars and the shockwaves from supernova can blow its gas reservoir clean away into intergalactic space, a process akin to a gentle breeze emptying a shallow pond. This stellar feedback halts the chemical enrichment process almost before it can begin. Without the deep gravitational well to hold onto its enriched gas, the dwarf galaxy is left starved, its potential for creating complex planetary systems severely limited. Therefore, a galaxy's initial mass sets it on a path, determining not just its size and brightness, but the very chemistry of its stars and the potential of its worlds. That central bar of stars is more than a beautiful feature, it is a powerful engine for change. Found in over half of all spiral galaxies, including our own Milky Way, a galactic bar acts like a vast cosmic mixer, stirring the galaxy's inner regions and fundamentally reshaping its destiny from the inside out. This process is known as secular evolution, a slow, internal transformation distinct from the violent, merger-driven changes we have discussed. The bar's immense gravitational field creates a powerful torque on the gas and dust clouds orbiting within the galactic disk. As these clouds encounter the bar, they lose a little bit of their orbital energy, causing them to spiral slowly inward toward the galactic center. Imagine the bar as a giant celestial spoon, slowly stirring the galaxy's inner pot and funneling its star-forming ingredients toward the central fire. This inward flow of gas has two dramatic consequences. First, it can trigger intense bursts of star formation right in the galaxy's nucleus, building up a bright central structure called a pseudobulge. Second, this relentless funneling action effectively steals the galaxy's future. By draining the inner disk of its star-forming fuel, the bar can eventually quench its own star formation, leading the galaxy toward a quieter, more passive state. This is evolution driven not by cosmic collisions, but by the galaxy's own internal dynamics, a gradual yet relentless metamorphosis written in the slow, gravitational dance of its stars and gas. Our solar system occupies a quiet celestial suburb, a location of profound cosmic fortune. We do not reside in the galaxy's bright, chaotic core, nor are we adrift in its sparse outer reaches. Instead, our Sun orbits about 27,000 light-years from the galactic center, nestled within a minor spiral structure known as the Orion Spur. This spur is not one of the grand primary arms of the Milky Way, but a smaller branch, a cosmic side street connecting the local stellar neighborhood to the immense Perseus arm. This specific position has been crucial for the development of life on Earth. The inner galaxy is a dangerous place, packed with stars and frequent supernova, all under the ominous influence of the central supermassive black hole. Its intense radiation would make stable planetary environments nearly impossible. Out in the distant halo, the stars are so ancient and metal-poor that rocky planets like our own may never have formed at all. Here in the Orion Spur, we enjoy a rare balance. The region is rich enough with the heavy elements forged in earlier stellar generations to build terrestrial planets, yet it is quiet and stable enough to allow those planets to exist for billions of years without being sterilized by cosmic violence. Our solar system's orbit is also remarkably circular, keeping us at a consistent, safe distance from the perils of the inner galaxy. This privileged address, this quiet corner in a vast spiral, is far from a random accident. It is the ultimate safe neighborhood, a stable platform upon which a planet could spend 4.5 billion years cultivating the intricate tapestry of life. The sheer scale of the cosmos presents a unique challenge for astronomers. With digital sky surveys capturing images of hundreds of millions of galaxies, how could a relatively small number of researchers possibly analyze them all? The answer came not from building a bigger supercomputer, but by tapping into a far more powerful resource, human curiosity. This led to the creation of Galaxy Zoo, a revolutionary citizen science project that invited the entire world to participate in cosmic discovery. Anyone with an internet connection could log on and be presented with a real, beautiful image of a galaxy from a telescope survey. Their task was beautifully simple: to classify its shape. Is it a spiral, an elliptical, or something more unusual? The response was staggering. Hundreds of thousands of volunteers from all walks of life began clicking, their collective eyes scanning the heavens from their home computers. In its first year alone, the project received over 50 million classifications, a volume of data analysis that would have been utterly impossible for any single research team. This was not busy work. The human brain possesses an incredible, intuitive ability to recognize patterns, often spotting oddities and anomalies that a pre-programmed algorithm might miss. Galaxy Zoo volunteers did not just sort galaxies, they discovered entirely new classes of objects. They spotted rare polar ring galaxies, identified strange overlapping systems, and flagged gravitational lenses that had slipped past automated scans. This collective effort proved that the universe is too vast and too wonderful for any one group of experts to understand alone. It demonstrated that the desire to explore and contribute to science is a universal human trait, and that by working together, we can all help to map the grand architecture of the cosmos, one galaxy at a time. Even in the wreckage of a cosmic collision, new worlds can be born. When two galaxies tear each other apart, their long tidal tails are not just streams of destruction. They are also rivers of potential. Within these drawn-out filaments of gas and stars, something remarkable can happen. Dense clumps of material, rich with hydrogen gas and sprinkled with ancient stars, can become gravitationally unstable. They begin to collapse in on themselves, just as the first proto-galaxies did in the early universe. These collapsing knots can eventually form their own independent, self-gravitating systems, complete with their own dark matter halos. We call these newborn systems tidal dwarf galaxies. Unlike the primordial dwarf galaxies that orbit larger hosts, these are second-generation objects, forged from the recycled debris of their parent galaxy's violent encounter. They are typically small, often no larger than a few thousand light-years across, and they are born with a unique chemical advantage. Because they form from gas and stars that have already been enriched by generations of stellar life and death, they possess a higher abundance of heavy elements from the very beginning. This gives them a head start in forming planets and potentially the complex chemistry necessary for life. The next time you see an image of two colliding galaxies with brilliant, arc-like tails, look closely at the knots of light within those streams. You are not just seeing destruction, you are witnessing a cosmic act of recycling on the grandest scale, where the death of two galactic structures gives rise to entirely new, independent islands of stars. Where a galaxy lives profoundly shapes what it becomes. This is the essence of the morphology-density relation, one of the clearest patterns in the cosmos. In the sparse, quiet fields of the cosmic countryside, far from the bustling crowds, spiral galaxies reign supreme. Here, they can spin in serene isolation, their delicate disks and gas-rich arms undisturbed, allowing them to continue forming new stars for billions of years. But step into a dense galaxy cluster, a sprawling metropolis of thousands of galaxies, and the view changes dramatically. The majestic spirals are almost entirely absent, replaced by the smooth, red ovals of elliptical galaxies and the enigmatic S0 galaxies, which look like spirals that have lost their arms. This is not a coincidence, it is a direct result of the environment's brutality. A spiral galaxy venturing into a dense cluster is like a delicate sailboat entering a hurricane. The cluster's immense gravity accelerates it to terrifying speeds, and it must run a gauntlet of dangers. It experiences constant gravitational harassment from near misses with other galaxies, which stirs up its internal structure and can strip away its outer gas. More devastatingly, it plows through the cluster's superheated intracluster gas, which acts like a cosmic pressure washer, scouring away its cold, star-forming fuel through ram pressure stripping. Without this gas, the spiral cannot make new stars. Its blue arms, once bright with youthful stellar nurseries, gradually fade. Its disk may be disrupted, its stars flung into random orbits, transforming its graceful shape into a smooth, rounded ellipse. The S0 galaxy represents an intermediate stage, a spiral that has been stripped of its gas and star-forming capabilities, but has managed to retain its disk-like structure. This powerful relation reveals that a galaxy's fate is not sealed at birth alone. Its form is a living record, a testament to whether it grew up in a peaceful cosmic village or survived the violent, crowded streets of a galactic city. Streaming through the emptiness between stars, an invisible rain of atomic fragments constantly pelts our galaxy. These are galactic cosmic rays, not rays of light at all, but the shattered nuclei of atoms, stripped of their electrons and accelerated to nearly the speed of light. They are the most energetic particles in the universe, and their origin story is written in the aftermath of stellar death. When a massive star explodes as a supernova, it does not simply vanish. It leaves behind an expanding shockwave, a colossal, spherical wall of energy and debris that races outward for thousands of years. This shockwave is the universe's most powerful particle accelerator. As it plows through the surrounding interstellar gas at millions of miles per hour, it creates a turbulent, magnetized frontier. Atomic nuclei, the raw material floating in space, get caught in this chaotic magnetic web. They are tossed back and forth across the shock front, gaining a little more speed with each crossing until they are flung into the void with unimaginable energy. These particles then embark on an epic journey, spiraling along the Milky Way's faint magnetic field lines, filling the entire galactic disk with a persistent high-energy fog. This cosmic radiation is a fundamental force within the galaxy. It heats the thin gas between stars, helping to determine the temperature and pressure of the interstellar medium. It can even trigger chemistry in dark molecular clouds, potentially helping to form the complex molecules that are the precursors to life. Yet for all their creative influence, these rays also represent one of the greatest dangers of space travel. For astronauts venturing beyond the protective bubble of Earth's atmosphere and magnetic field, this relentless subatomic shrapnel poses a serious risk. These high-energy nuclei can tear through DNA, increasing the long-term chances of cancer and posing a major challenge for any future mission to Mars or beyond. The same celestial explosions that seed the galaxy with the elements for planets and life also fill it with an invisible, energetic haze that both builds and threatens. The universe's vibrant era of star formation is a finite chapter in a much longer, darker story. All the brilliant stellar nurseries and blue giant stars are temporary phenomena fueled by a limited supply of cold gas. That fuel is being steadily consumed, and in the far future it will finally run out. The universe is destined for a slow, irreversible fade. Imagine a cosmic clock ticking down over trillions of years. One by one, the galaxies will exhaust their last reserves of star-forming gas. The great spiral arms, once traced by the brilliant blue light of newborn stars, will grow dim and indistinct. Without new stars to replace the old, the dominant color of every galaxy will shift decisively from blue to red, and then ultimately to black. The last generation of stars will be the small, frugal red dwarfs which can burn for trillions of years. But even they eventually will use up their hydrogen fuel. Their nuclear fires will sputter out, cooling them into cold, dark spheres of ash known as black dwarfs. The universe will become a cosmic graveyard, populated by the fading embers of stellar corpses, neutron stars and black holes, drifting in an ever-expanding, ever-darkening void. The grand dance of galaxy formation and evolution will have reached its final, silent state, a permanent twilight where no new stars are ever born again. Our entire galactic neighborhood is caught in a mysterious river of motion. The Milky Way, along with the Andromeda Galaxy and every other member of our local group, is not drifting aimlessly through the cosmos. We are all flowing toward a specific, hidden point in space, a region of such immense gravitational pull that it defies explanation. Astronomers call this enigmatic focal point the Great Attractor. It lies approximately 250 million light-years away, in the direction of the constellations Centaurus and Norma. This is not a single object we can see, like a star or a quasar. Instead, it is a colossal concentration of mass, a gravitational anomaly so powerful that it is tugging on our entire galaxy and thousands of others, drawing us in at a speed of over 1 million miles per hour. For a long time, its true nature remained shrouded in mystery, hidden from our view by the dense band of stars, gas, and dust that constitutes the plane of our own Milky Way. It was like trying to see a distant mountain range through a thick, permanent fog. Our own galactic disk was blocking the view of the very thing pulling us toward it. How do you study something you cannot see? The key lies in mapping the motion of the galaxies around us. By meticulously measuring the redshifts of thousands of galaxies, astronomers could trace the flow of this cosmic river, confirming that a vast, unseen mass was orchestrating this grand directional movement. Eventually, with instruments capable of peering through the galactic fog using X-ray and radio wavelengths, we began to pierce the veil. We now know the Great Attractor is not a lone monster in the void. It is the gravitational core of the Laniakea supercluster, an immense filament of over 100,000 galaxies to which our Milky Way belongs. At its heart lies the Norma cluster, a dense metropolis of galaxies whose combined mass creates a deep gravitational well. Yet, even this enormous cluster does not fully account for the strength of the pull we feel. The leading theory suggests that the Great Attractor is not a single point, but the center of gravity for an even vaster aggregation of dark matter, the invisible scaffolding upon which the entire supercluster is built. This dark matter halo, woven through with countless galaxies, generates the primary gravitational force that guides our cosmic journey. The mystery has deepened, however, as we have looked beyond it. Our entire supercluster, including the Great Attractor itself, is being pulled toward an even larger and more distant structure known as the Shapley Attractor, the most massive concentration of matter in our observable universe. So we are not just falling toward one mystery, but are part of a nested cascade of motion, a river within a larger river, all flowing through the darkness toward gravitational anchors we are only beginning to map. Our journey through these 50 facts circles back to a single, profound truth about our own existence. Every element in your body that is heavier than hydrogen and helium was forged in the heart of a star that lived and died long before our sun was even a glimmer in the cosmos. The iron that carries oxygen in your blood, the calcium that strengthens your bones, and the carbon that forms the foundation of your DNA were all created under immense pressure and temperature within stellar furnaces. These elements could not escape their stellar prisons during the star's life. Their liberation and our very existence required a cosmic catastrophe. It took the violent death of a massive star in a supernova explosion, or the collision of incredibly dense stellar remnants, to blast these newly forged elements out into the surrounding gas clouds. This enriched material, this stellar ash, then mixed with primordial hydrogen and helium, eventually coalescing into new generations of stars surrounded by planets. Our solar system and everything in it formed from this recycled cosmic debris. You are not just living in the universe is living in you. The carbon in your cells, the oxygen you breathe, and the iron in your blood are all tangible, physical evidence of galactic evolution. They are the direct descendants of those first stars that illuminated the early cosmos, the products of billions of years of stellar life, death, and rebirth. This grand cosmic story, spanning from the first quantum ripples to the collision of galaxies, is not a remote historical account. It is your own origin story, written in the very atoms that constitute your being. We are, each and every one of us, a way for the cosmos to know itself, forged from the scattered stardust of ancient suns. This connection is more than a poetic metaphor. It is a fundamental rewriting of our place in the cosmos. For centuries, humanity saw itself as separate from the universe, a special creation at the center of a celestial stage designed for our benefit. Now, we understand we are not merely inhabitants of the cosmos, we are an expression of it. The same physical laws that govern the spin of a galaxy and the collapse of a star also govern the biochemical processes within our own cells. We are not just watching the universe from a distance, we are a temporary, conscious arrangement of its most basic materials. This realization carries a profound sense of humility and belonging. Your ability to wonder about the stars is only possible because stars died to create the necessary ingredients for a wondering mind. The very act of looking up at the night sky is the universe gazing back at itself, contemplating its own origins and its own eventual fate. This cosmic perspective does not diminish our significance, it redefines it. We are a fleeting but integral part of an epic narrative that stretches across billions of years, a narrative written in the language of gravity, light, and time. We are the universe's way of experiencing beauty, asking questions, and feeling awe. In a very real sense, the cosmos dreamed us into being, and we are now its eyes and ears, slowly piecing together the magnificent story of our own creation. From the silent whisper of quantum ripples to the final fade of the last red dwarf, this journey through 50 cosmic facts reveals a universe in constant dynamic motion. We have witnessed galaxies born from chaos, sculpted by collisions, and guided by forces we cannot see. Their stories are not isolated but deeply intertwined, a grand tapestry where the death of one star gives life to another, and the merger of two giants creates a new celestial kingdom. This narrative stretches across 13.8 billion years, connecting the first spark of light to the conscious minds that now strive to understand it. So the next time you find yourself beneath a clear, dark sky, look up. See the band of the Milky Way not as a static painting, but as a living, breathing river of stars with a dramatic past and a transformative future. Each faint smudge of light is a distant galaxy telling its own chapter in this epic story. We want to know which of these 50 facts reshaped your understanding of the cosmos the most. Share your thoughts and carry this new perspective with you, a reminder that we are all citizens of a vast, evolving, and breathtakingly beautiful universe.